sklearn, model selection, time series split. Description: time series split is a cross-validation object designed specifically for time series data, where data points are ordered chronologically. It creates folds that maintain the temporal order of the data, ensuring that the train and test sets are always chronologically separated. Inputs: n splits, the number of splits folds to create. Max train size, the maximum size of the training set for each split. If none, the entire dataset will be used for training. Outputs: an iterator that yields train and test indices for each split. The train indices represent the data points used for model training. The test indices represent the data points used for model evaluation. Steps: the data is divided into consecutive folds based on the n splits parameter. For each split, the first max train size data points are assigned to the training set. The remaining data points are assigned to the test set. Metrics: time series split itself doesn't directly calculate metrics. It's used in conjunction with other evaluation methods like cross-validation scores, which measure performance based on the chosen model and evaluation metric, e.g. accuracy, R-squared. Visualization plots: you can visualize the splits using a time series plot, highlighting the training and test periods for each fold. This helps understand the data division and how the model is trained and evaluated. Fine-tune parameters: n splits adjust the number of folds to control the granularity of the cross-validation process. Higher values provide more folds but increase computation time. Max train size: set the maximum size of the training set for each split to influence the balance between training and testing data. Uncertainty methods: time series split itself doesn't directly handle uncertainty methods. However, the models trained using the splits can utilize uncertainty estimation techniques like confidence intervals or Bayesian methods for prediction uncertainty. Challenges and fixes. Challenge 1: insufficient training data in early folds. Sample use case that resulted in challenge 1: when n splits is large and max train size is small. The initial folds might have limited training data, potentially leading to poor model performance. Fixes to challenge 1. Consider reducing the number of splits n splits to ensure sufficient training data in each fold. Adjust max train size to increase the amount of data used for training in early folds. Challenge 2: data leakage. Sample use case that resulted in challenge 2: if the test set contains data points that are chronologically close to the training set, information might leak from the test set into the training process, biasing the results. Fixes to challenge 2. Ensure a sufficient time gap between the training and test sets in each split to prevent leakage. You can use techniques like rolling window or expanding window cross-validation to address this challenge.